think there must be still some people coming, but let's get started. So today we're very happy to have Wolfgang Altmannshofer from the University of Santa Cruz. Wolfgang did his PhD with Professor Buras in Munich and finished in 2010, and then went on for postdocs at Fermilab at the Perimeter Institute, and first took up a faculty position at University of Cincinnati, and since 2018 he is a faculty member at the University of Santa Cruz. So Wolfgang is an expert on B physics and flavor physics more generally. He worked a lot on B to S transition, but also many other processes there. And today he will tell us about the state of the B physics anomalies. So yeah, please, Wolfgang.
Thanks for the introduction. Also, thanks for the invitation. It's always fun to talk about the B anomalies. Let me share my screen. Okay, here we go. Yeah, so I will talk a bit about the B physics anomalies. These anomalies have been around for many years now, and what makes them very interesting, in my opinion, is that we not only have these anomalies in a handful or half a dozen of observables, but they can be explained in a very simple and consistent way by new physics. And that's by itself is actually a non-trivial statement. So not every time you have an anomaly, it means that it can be explained by a new physics effect, in particular if there are several of discrepancies between standard model predictions and measurements. But in that case, in the case of these B-decay anomalies, the experimental data seems to be in very good agreement with a very simple new physics scenario, and that's what, in my opinion, makes this very intriguing. So what I will do in this talk, I will go through the current state of those B anomalies, and then I will spend quite some time in trying to explain what could be behind those anomalies in terms of the physics, which type of new physics models could lead to those effects. Let's start very basic. So what is the basic principle behind searching for new physics with these rare B decays? So when I talk about rare B decays, what I'm referring to are flavor changing neutral current transitions. The example here that will be the main topic of the talk will be a transition from a B quark to a strange quark and a muon anti-muon pair. And in the standard model, such a transition is generated at the loop level. Here's one example of a loop diagram with a top quark and a W boson. And that means that in the standard model, these type of transitions are strongly suppressed. They are suppressed by a loop factor, and they're also suppressed by small CCAM matrix elements. So these rare decays are rare because of these suppression factors. But then on top of the standard model contribution, there could be an additional new physics contribution that one can parameterize in a model-independent way by just some 4 fermion contact interaction, which leads to this B to S mu-mu transition. And then the basic idea is very simple. One measures these type of transitions as precisely as possible. One calculates the standard model prediction as precisely as possible. And then one compares those two things. And in that way, one gets information on a possible new physics contribution. If the measurement and the standard model prediction agree, then one can get constraints on possible new physics contributions. If there's a discrepancy, then one could have an indirect evidence for the presence of new physics that shows up in those rare decays. The interesting point is that one can use the information from the rare decays to infer a scale of new physics. So if one parameterizes this contact interaction, this B to S mu contact interaction coming from new physics in terms of a new physics coupling and a new physics scale, and if one just very generically sets the new physics coupling to 1, and if you also assume that there's an order 1 discrepancy between the measurement and the standard model prediction, then one can infer that the new physics scale that could be behind the discrepancy is of the order of around 10 TeV. And that's a very interesting scale. It's a scale that's potentially above the direct reach of the LHC, but not too far above that it couldn't be in reach of potential future colliders. So that's a very interesting energy range. So if there's a discrepancy in this rare B2S mu transitions or B2S LL transitions, and if this can be established in a robust way, then one can expect new physics at those scales of maybe tens of TeV, and those would be then a potential target for future direct exploration. Now on the experimental side, the main player is the LHCb experiment. What is shown here is the integrated luminosity of LHCb over the past decade. So we're having something like a 3+6 inverse femtobarn of integrated luminosity that have been recorded, something like 10 to 12 B quarks. And LHCb has therefore very unique sensitivity to many rare B decays. So the statistics that is available at LHCb is much larger than the one at the past P factories, and also statistics that is expected at BEL2. So if there's a rare decay which has a clean signature, then LHCb has this very unique sensitivity, and many rare B decays have now been measured very precisely by LHCb. In terms of the anomalies, I like to sort them into this chart here, which on the x-axis shows the quoted significance of the anomaly, and on the y-axis something that I call relevance of hadronic effects. So you can think of it as a quantity or as a scale which tells you how much you should trust the significance that is quoted, at least from a theoretical point of view. Though ideally you want to be in the upper right corner of those plots. So you want to have high significance, and you want to have very little relevance of hadronic effects in order to trust the theoretical predictions that one compares the experimental data to. And though what is now inside this chart are these various observables that show discrepancies between data and standard model predictions. On the one hand, down here are various branching ratios of rare B decays that are based on the B2S mu transitions. One has B2K mu, B2K star mu, so B sub S to phi mu, and these branching ratio measurements, they differ from standard model predictions by 2 to 3 sigma or so. However, they are subject to hadronic corrections, so the theory predictions do have uncertainties, and it's not always clear how well controlled certain hadronic effects are, and how well estimated the theory uncertainties here are. What is also on this chart here are B2K star, the B2K star angular distribution, an observable called P5 prime, and we will come back to that later in the talk. That is, from the theoretical point of view, a bit cleaner, and again there's a discrepancy at the level of 2.5 to 3 sigma in the angular distribution of B2K star mu. We also have the branching ratio B sub S to mu. That one is, from the theoretical point of view, a bit cleaner. The only thing one needs to know there is a B-meson decay constant, which is pretty well known from lattice QCD calculations. And there again, there's something like a 2 sigma discrepancy between the standard model prediction and the measurements. And then up here, the theoretically most clean observables are so-called Lepton flavor universality ratios. On the one hand, RD and RD star, those are ratios of semileptonic decays, B2 charm transitions, B2 charm L nu transitions. They have discrepancies with standard prediction between 2 and 3 sigma or so. And then RK and RK star, probably the most famous or prominent ones in the context of B2S LL transitions. These are these Lepton flavor universality ratios where one compares B2S mu transitions with B2S EE transitions. So these are ratios of branching ratios of B2K mu or B2K EE and B2K star mu or B2K star EE. And they are arguably the theoretically cleanest observables that one can construct in the context of these types of decays. Again, to emphasize is that before these RD and RD star observables, they are related to transitions from a B quark to a charm quark in the lepton and the neutrino. These are charged current decays, while the ones inside the red circles, these are decays based on flavor changing neutral current interactions, B to S LL decays. In the talk, I will focus on the flavor changing neutral current decays. Yeah, so let's go through them, through these anomalies, and see what we can learn from them. The first thing I want to discuss is the B sub S to B plus B minus decay. To be the simplest of these types of transitions. We have a bound state of an anti-B and a strange quark decaying into a muon and an anti-muon. And what one basically has to do on the experimental side, one looks for a bump in the dimuon invariant mass spectrum at the mass of the B sub S meson. Here's a plot from LHCb, which clearly shows that there is this bump in the data. The x-axis is the dimuon invariant mass, and one sees this very nice peak at the mass of the B sub S meson. And the branching ratio that one can then extract, what is shown here is a combination of LHCb, CMS, and Atlas results, is around 2.7 times 10 to minus 9, which is close to the standard model prediction, which is around 3.7 10 to minus 9. But given the already pretty small uncertainties, it's something like a 2.5 tension between the standard model prediction and the experiment. Soon we will get updates on this branching ratio. So as far as I understand, next week there will be a seminar at CERN, and I expect to see updates from LHCb on that branching ratio. Although the current LHCb analysis, I think, is done with only the data up to 2016, though we can expect an improved precision from LHCb on this branching ratio once they show results with a full run-2 data set. The next type of decays to look at will be semileptonic decays, B to S mu transitions. Here an example of a B to K mu decay. So now we have a B quark going into a strange quark in the muon anti-muon, and we have an up quark or anti-up quark here as a spectator. And there are various versions of that. Instead of the anti-up quark as spectator, we can have the anti-down quark as a spectator, or we can have an anti-strange quark as a spectator. And shown here are now examples of measurements of branching ratios, now as a function of Q squared, where Q squared is the dilepton invariant mass squared. All these are differential branching ratios as a function of Q squared. And what is compared in these plots are the theoretical predictions, the various green or blue bands shown in these plots, and they're compared to the experimental measurements with the black crosses. Most precise measurements come from LHCb, and on the clear trend here that the experimental results are lower than the standard model predictions over a broad range of Q squared values. So both for B to K mu transitions, which is this plot here in the upper left. If we can look at B to K star mu transitions, that is a plot in the upper right, and also B sub S to phi mu in the lower left. In all those cases, the experimentally measured branching ratio seems to be below the standard model predictions. Now, one thing one can see also in these plots here is that the uncertainties, the quoted uncertainties on the standard model predictions, they actually vary quite drastically here if one compares the predictions for B to K mu and here B sub S to phi mu. So the width of those standard model bands is quite different, and indeed it depends which standard model prediction one uses there, and there are certain hadronic effects that need to be taken into account. There are form factors that need to be known in order to make standard model predictions, and it's not always entirely clear how to estimate how big the standard model uncertainties are. So depending on what you do precisely, the significance of the discrepancy will change. Let's go one step further and look at yet another type of decays. Now I want to focus on B2K star mu decays. So now we have a B-meson decaying into an excited kaon, and a mu and anti-mu parent, and an excited kaon decaying further into a kaon and a pion. It's the same B2S mu transition as before, but now with this intermediate excited kaon. We have now a 4-body final state in this event, and one can have access to various angular observables. So one can measure the angular distribution of these decay products and get information on a variety of aspects of the B2S mu transition that is underlying such a process. Just as an illustration, here's an event display of how such a decay looks like in the LHCb detector. So one has the primary vertex where the B-meson is produced. So one has a secondary vertex here where it decays, and one can clearly see the 2 muons coming out, and also the pion and also the kaon, and they all point back to this secondary vertex. So what you want to do is to take the invariant mass of those 4 particles, and they should give back the mass of the B-meson, the mass of the invariant mass of the K and the pi. They should give the mass of the K star. And then you can look, for example, as was done before in the previous slide, you can look at the differential branching ratio as a function of the muon invariant mass. But we can also look at various other observables, angular observables, that basically moments of the angular distribution of those 4 decay products. And one famous example is this observable P5 prime. I didn't put the exact definition here, but it's you can think of it as a moment of the angular distribution. What is shown here is the P5 prime observable as a function of Q squared, the dimuon invariant mass squared. And what is shown here is a situation from 2015. The orange and purple boxes here are standard model predictions. And then the various experimental results are overlaid here in this plot. The most precise ones come from LHCb, the black crosses here. And even though there's quite some scatter in the experimental results, if you make an average of them, you find a pretty significant deviation between standard model predictions and the experimental results in those 2 bins, in particular in this bin from 4 to 6 GeV squared, and in the bin from 6 to 8 GeV squared, and something like a 2.5 sigma effect in both of those bins. Now, recently, something like a year ago, there was an update of the angular distribution measurement by LHCb. The update of the P5 prime measurement is shown in this plot here. Uncertainties have gone down quite a bit. The central value shifted a bit to the standard model central value, but overall, one still has an anomaly here. This anomaly persists, including also the 2016 data from LHCb. And it's again something like a 2 to 3 sigma discrepancy in those two Q squared bins. A few months ago, there was another interesting result that came out from LHCb, and there they are looking at the decay of charged B-meson into charged K stars, M plus or minus. So the result that I've shown in the previous slides was for neutral B-mesons going into neutral K star and M plus or minus, and they also see this anomaly in the charged decay mode, even though the uncertainties there are much larger. The trend is the same as before. The measurements here, they lie above the standard model predictions, even though the significance here is not as high as in the case of the neutral decay mode. The central values are very well compatible with what is seen in the neutral decay mode. Finally, let me also show the results of the Lepton flavor universality ratios. As I mentioned before, we're talking here about these ratios RK and RK star, ratios of branching ratios, comparing muons with electrons in the final state. They are shown here. RK and RK star again is function of Q squared. The standard model prediction for those ratios is 1 with very high precision. And the experimental results are summarized here. These are the results from LHCb. In case of RK, the latest result, which includes also 2016 data, is around 0.85 with around 0.06 uncertainty. That's something like 2.5 sigma away from the standard model prediction. And then for RK star, there are 2 Q squared bins where the results are available. And in those 2 Q squared bins, the result is around 0.7 with uncertainties of around 0.1. So again, 2.5, maybe even 3 sigma discrepancy with respect to the standard model predictions of around 1. There's also an interesting result on baryonic decays, lambda B baryons decaying into proton and kaon, and 2 leptons. Also there, the lepton universality ratio is measured. The essential value is within uncertainty is compatible with the standard model, but here the uncertainties are a bit larger. So it's compatible with those results for the meson decays, but also compatible with the standard model prediction. Now, as far as I know, also for RK, we will see updates next week. So that will be interesting to see if the discrepancy persists or if that result moves closer to the standard model prediction. So the hope is that with the full run 2 data set, that this significance of the discrepancy increases from 2.5 sigma, maybe above 3 sigma. But this, you have to see what will happen once the new results are shown. Oops. Okay, one comment I want to make about the RK and RK star predictions in the standard model. As I mentioned before, they are predicted to be 1 in the standard model. It's very high precision. So how well do we actually know that, or what are the things one might need to worry about? The first thing is the only thing that really in the standard model at the level of the Lagrangian, let's say, distinguishes between muons and electrons are phase-space effects. The mass of the electron and the muon is different, but because B-mesons are much heavier than muons or electrons, these phase-space effects they are tiny. They are completely negligible for large Q squared values. It's a very low Q squared region. It's a very low Q squared region. They can be relevant. There are a few percent, but this can be taken into account. Now, these hadronic corrections that I had mentioned before in the context of the branching ratios and also the angular observables to some extent, those are canceling out in the ratio of the branching ratios up to the effect that there are phase-based differences. So even though there are hadronic corrections to the branching ratios, say, once you look at their impact on RK and RK star, their effect is suppressed by this tiny phase-based effect. So it's basically completely negligible. What can be relevant are QED corrections, because of soft and collinear photon emission, the branching ratios or the decays with electrons and muons in the final state, they do behave very differently when QED corrections are taken into account. So a very naive way of estimating them would be that they should be proportional to the fine structure constant times logarithms that compare the electron mass to the muon mass. In reality, these logarithms are much smaller because one has to take into account the relevant experimental cuts that go into the analysis. And in fact, people have been looking at that in quite some detail. And these QED corrections, they do seem to be under control at the level of the total rate at least. And what those studies find is that indeed RK and RK star, they are 1 with very high precision, at least in this Q squared bins above 1 GeV squared. One can very well approximate RK and RK star with maybe a 1% uncertainty. In the low Q squared bin of RK star, so one has to take into account these phase space effects, and there's probably a slightly larger uncertainty. So here's the standard model prediction of around 0.91 plus or minus 3% or so. If one looks at the differential level, then there might be larger QED effects. So I guess it is something one needs to be aware of if one looks, for example, at angular distributions in a lepton in a lepton universal testing way. If one compares angular distributions in B2K star mu mu with B2K star E, for example, this is something one needs to be aware of. Now, what could those anomalies be? So discussed a bunch of them. We looked at the rate of B sub S plus or minus. We looked at the rate of the various semileptonic decay modes. We looked at these angular observables, in particular P5 prime, and we also looked at the lepton flavor universality ratios. Experimental issues could be behind that. Maybe I'm not qualified, I guess, to talk about this aspect. Could be statistical fluctuations. Each single one of them is at the level of, let's say, between 2 and 3 sigma or so. So it could be that just a situation where some of those statistical fluctuations, they just happen to pile up in the context of these rare decays. It could be parametric uncertainties. In some cases, yes. So in case of B sub S plus or minus, I think I had mentioned that one needs to know the B-meson decay constant. That is arguably pretty well known. So it would be a surprise if that uncertainty was largely underestimated. Another thing that enters there are CKM matrix elements. So one needs to know the CKM element BTS, which is related to VCB, and there's some uncertainty in VCB. There's even some discrepancy between different ways of extracting VCB from the data. So it might be that there are underestimated parametric uncertainties, which at least in part drive the discrepancy in B sub S plus or minus. And similarly, it could be that also in the semileptonic rates, parametric uncertainties are the cause for at least part of the discrepancy that is seen. Angular observables and lepton flavor universality ratios, they are constructed such that these parametric uncertainties are coming from, let's say, CKM matrix elements or decay constants or overall normalization of form factors. Those things, they all drop out. So those observables are constructed to be insensitive to these types of uncertainties. But there are other things that one needs to worry about. Hadronic effects that I had briefly mentioned in the context of the rates. B sub S plus or minus is insensitive to these things, but the semileptonic rates and the angular observables in B2K star mu, they are sensitive to hadronic effects, which are hard to describe theoretically. And it might be that certain effects here are underestimated, and one could attribute some of the discrepancies in the semileptonic rates and the angular observables to such hadronic effects. Lepton flavor universality ratios, on the other hand, again, they are robust against those things. And finally, the most interesting or most exciting possibility is that it's new physics, which is behind that, and potentially new physics could explain all of those. And in all generality, of course, it could be a combination of all of those things. Now, let's assume there is new physics behind these anomalies, and let's try to figure out in a model-independent way which type of new physics it could be. And one way to do that, or probably the most systematic way of doing it, is to introduce an effective Hamiltonian, and introduce higher dimensional operators, which could contribute to B2S LL transitions. Those type of operators are very well known and understood and classified. One distinguishes several classes of operators. There are dipole operators. They come with coefficients that are called C7 and C7 prime, depending on the chirality of the bottom and strange quark involved in this interaction. They're so-called semileptonic operators for fermion contact interactions, which have either a vector current or an axial vector current for the muons. The corresponding couplings or coefficients of those operators are called C9 and C10, or C9 prime and C10 prime, again, depending on the chirality of the involved bottom and strange quarks. And then there are also scalar operators, where one has a scalar currents with the muons and the B to S transition. And what is important here is that these various operators, they enter different decay modes in a characteristic way, and they enter different observables in those decay modes in a characteristic way. So what is shown here in this table is just a very a very loose characterization of which observables or which decay modes are mainly sensitive to which types of new physics effects. If there's new physics that shows up as one of these coefficients of these dipole operators, these B2S gamma operators, they will mainly, they can largely affect the B2S gamma transitions, either the inclusive or exclusive decays of B-mesons, also the B sub S to phi gamma decay. But they can also modify the semileptonic ones by a photon going into plus or minus or E plus E minus. The semileptonic operators, C9, C9 prime, C10, C10 prime, those are very relevant if one talks about the semileptonic decays. And also the B sub S to plus or minus decay is sensitive to C10 and C10 prime. Then the scale operators, they play mainly a role in this purely leptonic B sub S to plus or minus decay. Once one takes into account the constraints that one gets on those scalar operators from B sub S to plus or minus, they can have very little impact on the semileptonic B2S LL transitions. However, what this table illustrates is that there are many different decay modes and many different observables within each decay mode that are affected simultaneously if one switches on a specific coefficient. So what one needs to do is one needs to perform global fits in order to figure out which type of coefficients is either preferred by the data or to which extent these coefficients are constrained by the data. And I've been doing this for actually quite some time already. I started doing that almost 10 years ago, a long time before there actually were anomalies in those rare B decays. And the original idea was just to constrain possible new physics in these types of decays. But then the anomalies started to show up over the years. And by now there are many, many groups who actually do these types of global fits, trying to understand which type of new physics interaction can be behind the pattern of deviations that is observed. And yeah, here's a list of the most recent studies. So what I'll be showing is mainly based on my last work from around 2 years ago, but all the plots that I'll be showing are updated with the most recent data. And yeah, so here's the first set of results that I want to show. This is just in terms of a table. What we are doing here is we're switching on one of those new physics operators at a time, and then we look what is the best fit value for a given coefficient, and how much better does this new physics scenario do compared to the standard model. So, for example, here in the first line, it shows when you switch on a new physics interaction parameterized by this coefficient C9, you find a best fit value of around -1, and you get a square root of delta chi-squared of 6.4. So this new physics scenario does much, much better than the standard model in describing all the available data on those rare B decays. Similarly, also very successful is a scenario where you have both C9 and C10 simultaneously, and you put them in a specific relation. So if you say C9 is switched on and C10 is switched on with the same magnitude but with a relative minus sign, that corresponds to new physics that couples to left-handed quarks and lepton currents, which is something which is well motivated from a UV point of view. And in that case, it's even something like a 6.9 of a square root of delta chi-squared that you get comparing standard model to this new physics scenario best fit point. So when there's very high preference for these non-standard values for C9 and or C10, and now these precise values for this delta chi-squared, those depend on which theoretical uncertainties you are putting into the analysis, into this global fit. So if you trust the theory errors that we are using, then you get these values above 6. If you don't trust them and make them and increase them by a factor of few, then you can bring that down to around 4 or so. And that is then mainly driven by the Lepton flavor universality ratios, which are largely insensitive to any theory uncertainties. Also, one thing I should mention, so what is shown here in this table are coefficients that affect the decays with muons. I can also try to explain the data by affecting the decays with electrons. In that case, one can only explain RK and RK star, but not the other observables that show discrepancies because they are specific to the B2S mu transition. I can also look at that in a two-dimensional way. So now we're switching on 2 Wilson coefficients or 2 of those neophysics interactions at a time. Here in this plot, I show on the x-axis C9 and on the y-axis C10. Again, in the B2S mu transitions and no neophysics in the B2S E transitions. For comparison, if you see these values here on the axis ranging between around -2 to 1 or so, in the standard model, these coefficients are around 4. So we're talking here about order 1 neophysics effects in those decays. And what is shown here now is on the one hand, in this purple ellipse is the are the results on the B2S mu angular distribution. So that includes in particular P5 prime, which shows the discrepancy, and this discrepancy in P5 prime that prefers a coefficient C9, which is the physics contribution to the C9, which is negative around -1 or so. That's a destructive interference with the standard model by a physics contribution, which is something like 25% of the standard model contribution. What is also shown in blue are the branching ratio results, so the B2K mu, B2K star mu, and B sub S to phi mu branching ratios, which are low compared to the standard model. And those branching ratio results, they prefer, well, to get this banana-shaped region here in this Wilson coefficient space, and you get a nice overlap at the 1 sigma level out here for a C9 of around -1. So there's a strong preference combining these data sets for a negative C9, and there are maybe some small hints for a positive C10. And yeah, that's when you combine those two sets. If you take into account both the angular distribution and the branching ratios, combine them, these are now the 1 and 2 sigma contours for the best fit region. You can also add in information from baryonic decays, lambda b to lambda mu. Then one gets a slight decrease in the tension with the standard model. So standard model is here at 0, 0. So taking into account these baryonic decay modes, the essential value moves a bit closer to the standard model. Yeah, so that's the combination of all B2S mu transitions that are available at the 1 and 2 sigma level. Now, what else can we add to that plot? Now we add in the Lepton flavor universality ratios, RK and RK star. Here shown the 1 sigma contours. In case of RK, this very elongated band here. Similarly, also for RK star, one gets a pretty long band that extends actually up to quite large values of these Wilson coefficients. But there is this nice overlap with the results on the B2S mu decays by themselves, the angular distributions and the branching ratios by themselves. So it finds that there's this nice overlap region where all those things can be explained simultaneously. And yeah, it's just combining them in a slightly different way. Now there's a combination of RK and RK star at the 1 and 2 sigma level, and one sees here this even though there's no overlap at the 1 sigma level, at the 2 sigma regions, they nicely overlap. What else? B sub S to be plus or minus. If we add this in, B sub S to be plus or minus, this discrepancy there between standard model and data, that prefers a positive value of C10. That gives this yellow band in this plane here. Again, it's in the same region as all the other preferred regions. And then if you combine the Lepton flavour universality ratios with B sub S to plus or minus, which arguably are the cleanest of those observables, you get this blue region here, and then all the rest, the B sub S to the B to S mu transitions, which arguably are theoretically under burst control. You get this orange region here of before, and again, one sees at 2 sigma there's a nice overlap, even though the clean observables, they prefer a positive C10, and the B to S mu observables, they prefer a negative C9. If one does a global fit combining everything, one ends up with a situation where one has very good description of the data if one has a negative C9 and a positive C10 roughly of the same size. But we can also have other scenarios. Even the scenario if one only has C9 works very well. And scenarios where one only has C10 also work very well, even though one doesn't explain all the anomalies in the data. One still gets a very good overall quality of the fit also in those cases. So what are the implications for the near physics scale in if one takes these discrepancies seriously? So this is just a simple exercise here. If one switches on just this one operator, which corresponds to the Wilson coefficient C9, so this is a vector current for the muons, and if one just asks what are the generic values for the near physics scale that correspond to the best fit regions in that case, then one, well, the answer depends on what one assumes was a coupling that one puts in. So if one says the coupling should be of order 4 pi, then one gets a sort of the largest possible near physics scale, and that's around 120 TeV. So if one takes this 4 fermion contact interaction, this B to S mu contact interaction, and one is able to directly probe it at the scale of 120 TeV, one would be able to resolve what is behind that contact interaction. So by once you reach 120 TeV, you can sort of be sure that you are able to figure out what type of near physics is behind that. If you assume that near physics is more weakly coupled, then you get, depending on what you assume exactly, if you also assume that there's CKM suppression or loop suppression or both CKM and loop suppression, you get values between tens of TeV and several hundred of GeV, whereas the near physics could be that could lead to the observed effects. In terms of concrete models, my favorite model is based on gauging the difference of muon number and tau number. So that's an anomaly-free global symmetry of the standard model Lagrangian, which can be gauged, and the corresponding gauge boson, the corresponding Z prime, couples to muons in a vectorial way. So one gets this Wilson coefficient C9, and then one can couple this gauge boson also to quarks by having it mixed with some heavy vector-like quarks, which are probably in the mass range of a few to several TeV, maybe 10 TeV or so. And in that way, one can actually construct a toy model which very nicely fits this effective description in terms of the operators that I've shown before. And one thing that I need to point out in that context, actually the first time we proposed this type of model was before the RK and RK star measurement came out. So originally our idea was to explain the P5 prime anomaly, which which was already out there at that time. And actually, in our paper, we had actually a prediction for lepton universality violation, which then matched up very nicely with the measurement by LHCb of RK and RK star, which came afterwards. Now this C prime model is very strongly constrained by existing data already. So if we look at the parameter space of this model in terms of the mass of the C prime and the gauge coupling, one can find that in this white region up here, one can explain the B anomalies, but there are various constraints that one needs to take into account. There are strong constraints from B sub S mixing, which include everything down here, and there are very strong constraints from neutrino scattering experiments, also from G-2, from direct searches at the LHC, and also at B factories. So one is constrained to a rather narrow region of parameter space in this model. One interesting side remark, this model could in principle also explain G-2 of the muon, the anomaly, the long-standing anomaly in the G-2 of the muon. However, it only works for a very, very light C prime. The mass of the C prime, in order to explain G-2, has to be around 100 MeV or below. And in that mass regime, it cannot explain the B anomalies. So in order to explain the B anomalies, it has to sit up here, roughly above the significantly above the mass of the B-mesons themselves. In another comment about lepton flavor universality in this type of models where one gauges muon number minus tau number, a very clean prediction of that model is that the C prime couples to muons with a gauge coupling that I call here G prime, and it couples to taus with the same gauge coupling but with an opposite sign. So what this model predicts is that one should see opposite effects in mu plus mu minus and the tau plus tau minus final states, and one should have no effect in the E plus E minus final state. So the B2S EE transitions, they should be completely standard model-like. B2S mu transitions, they can be affected, and then the B2S tau tau transitions, they are affected in the opposite way, comparing to mu plus mu minus final states. The problem there, of course, is that on the experimental side, it's very hard to make precision measurements for decays with taus in the final state. But sort of the smoking gun prediction of that model would be that if you measure a lepton flavor universality ratios of say B2K tau tau or B2K EE, then this should be enhanced by something like 20% or so, which corresponds to a 20% suppression of mu mu versus EE. In the context of these models, one can make predictions for many lepton flavor universality observables. So we looked at those ratios of branching ratios, RK star. One can look at other mesons, B sub S to phi mu mu, B sub S to phi EE, etc. as well. And we can also look at angular observables, differences of angular observables between, let's say, B2K star mu mu and B2K star EE. One can take particular P5 prime and compare the P5 prime for the muons and for the electrons and try to find if there's a difference between those. One can also look at similar things for other angular observables, things like forward-backward asymmetries or longitudinal polarization fractions of the K stars. And one can, for all those types of observables that are accessible from the angular distribution, one can define these differences, these lepton flavor differences, and test if lepton flavor universality is violated in those decays. And on this slide, there's a set of predictions one can make for these lepton flavor universality differences in these models based on L mu minus L tau. This red dotted line is a standard model prediction, which is close to 0 for most cases. And then with these, in this blue band, these are the 1 and 2 sigma predictions for that model. Same thing here with the branching ratios, the branching ratios. So RK star, R phi, also the ratios of inclusive decay modes here. Again, the red dotted line is a standard model prediction, and then the blue bands are the model predictions of this L mu minus L tau model. And what I've overlaid here is the experimental result on RK, which came out in 2015. This was the first result on RK that came out. And then when I looked back at those predictions, and if we look at the current situation, it works even better. So our predictions from 2015 now work extremely well with the latest RK measurement, and also the RK star result lines up very nicely on those predictions. So I'm very curious to see what future updates of RK and RK star will look like, and how well this model actually will describe the data. There are a bunch of other predictions that one can make based on those models that gauge muon number minus tau number. One interesting aspect is that they suppress lepton flavor violation. So they do have lepton flavor universality violation, but they don't have actual lepton flavor violation in their model setup, and that is because of the L mu minus tau symmetry. The lepton Yukawas and the couplings of the C prime are aligned. So that means that one predicts negligible rates for processes like B sub s to tau mu or B to k star tau mu. And this is very different to many other models that have been suggested to explain the B anomaly. So many of these leptoquark models which have been suggested, they predict very large rates of B sub s to tau mu and B to k star tau mu. But this type of model does not. So those decay modes should be absent. Also, this model predicts that there shouldn't be any new physics effect in B sub s plus V minus. So I've shown before that there is some discrepancy also there at the moment. And there again, it would be very interesting to see updates. If it's the L mu minus tau model which is behind the anomalies, this anomaly should go away because the prime in that model couples vectorially to muons. It cannot explain any deviation in B sub s plus V minus from the standard model prediction. And again, that's in contrast to many other models that have been constructed. And finally, another interesting aspect is looking at B2K and B2K star new decays. So it decays now with neutrinos instead of charged leptons in the final state. In the L mu minus tau model, one suppresses the decay mode with the muon neutrinos and one enhances the decay mode with the tau neutrinos. And the decay mode with the electron neutrinos remains unaffected. So if you take into account that one cannot measure actually the neutrino flavor in these types of experiments that look for these rare decays, one finds, well, one has to sum over all those neutrino flavors. And in the end, in that model, in the L mu minus tau type of models, one finds that B2K nu and B2K star nu is standard model-like to a very good approximation. And again, that is in contrast to many other models that predict that this decay mode should be enhanced with respect to standard model predictions. So my prediction based on this class of models is that there shouldn't be any lepton flavor violations. There shouldn't be any new physics effect in B sub s plus minus. So I predict that this will go back to the standard model. And I also predict that B2K star nu and B2K nu will come out standard model like once they're measured by Bell 2. One can extend the L mu minus tau model. I think I'm doing this time. So I have a few more minutes, so let me say a few more words about these type of models. So one can try to see how robust these predictions are that one has there, and one can try to extend it in a consistent way. And as long as you don't go too crazy, so if you consider a certain set of rules, so if you still want to allow standard model Yukawa couplings at a realizable level, if you want to forbid lepton flavor violation, because as it seems, at least we don't have any indications for that. And if you only allow for 3 standard model singlets in order to cancel gauge anomalies, then one finds that there's a 4-parameter family of possible U1 gauge symmetries, basically a linear combination of hypercharge, then a baryon number over 3 minus electron number, baryon over 3 minus muon number, and baryon number over 3 minus tau number. And one can gauge any linear combination of those symmetries. And if one does that, one interesting aspect that one finds is that one not only gets now these C9 operators, which can be lepton flavor non-universal, but one also gets now C10 operators. So one can, in principle, get new physics effects in B sub S semi plus C minus. However, these new physics effects in C10, they are necessarily lepton flavor universal. That's just a result of those assumptions that we are making here. Also, once you introduce these axial vector couplings, it turns out that they necessarily lead to mixing of the Z and the Z prime, and man gets actually pretty strong constraints from electric precision observables. So one can extend these Muir-et-al models in a consistent way, but one is sort of restricted of what one can do there. Finally, maybe what is interesting are the future prospects for these types of lepton flavor universality tests. What is shown here in this plot is sort of a timeline of the expected precision on a bunch of observables, RK star, also R phi and R pk, so the baryonic version of these lepton flavor universality ratios. And one sees that with sufficient statistics, both LHCb but also BEL2 will be able to make a few percent to make a measurement at the few percent level for RK and RK star, and ultimately even might reach a sort of like a 1% precision for RK and RK star. And with these types of statistics that will be available then from later runs, one can also then look at lepton flavor universality tests with angular distributions, like the ones that I had shown in a previous slide. One very last thing that I also wanted to mention, there's one nice aspect where one can also check lepton flavor universality. That's in phi decays. So it turns out that lepton universality in phi decays is not very well established. So there are some measurements of lepton flavor universality in phi decays, but it's only known to, let's say, with less than 10% precision or so. So a few years ago, we actually suggested that that is something that LHCb might be able to do. If you look at phis coming from B-meson decays, one should get tens of thousands of those phis, and one should be able to measure lepton universality in phi decays, maybe with a 5% precision or so. And in that case, this would lead to the world's best results on lepton flavor universality in phi decays. That's just as a curious side remark at the very end. So here's my summary. As I've discussed, current rare B decay data shows various intriguing discrepancies with standard predictions. They show up both in branching ratios and also in angular observables. They could be new physics. They might be also due to underestimated hedonic effects. But once we look at lepton flavor universality ratios, then those are theoretically very clean. And interestingly, they are very nicely compatible with the other anomalies. And if the significance for these lepton flavor universality ratios, for the violation of lepton flavor universality in those ratios grows with more statistics, and this would be a very clear indication for new physics. Possible new physics model would be gauging of humans at tau, but one has to see if the predictions of that model will remain compatible with future data. And and hopefully with more data from LHCb, maybe also Atlas and CMS, and certainly also BEL2, with more data from all those experiments, it should be possible to sort out what's going on here. All right, that's all I had. Thanks.
Thank you very much, Wolfgang. So now we have time for questions. Who wants to ask questions? Maybe just if you're online, just speak up because I don't see everyone. How about I start us off? So I have one question about your model. So you said that basically, in order to explain the physics anomalies, you have to be above 10 GeV for the mass. Can you expand a little bit more on that?
Yeah, the precise number. Yeah, So this precise number 10 GeV is just a bit arbitrary. So what one has what is a necessary condition is that the C prime has to be heavier than the B-mesons. Otherwise, the B-meson would decay into an on-shell C prime, and then you would see a prominent bump in the dimuon invariant mass spectrum in the B decays.
Mm-hmm.
So that doesn't work. Now, how heavy exactly you have to be I don't think anybody has studied that in lots of details. 10 GeV is just a rough guess of where I believe the boundary probably is. If it's anywhere below that, then you probably will see the tail of the C prime bleeding into the Q-square distribution of those B decays.
Okay, thanks.
Sorry,
Rupert.
U-10 model as well. First, just say, Wolfgang, thanks a lot for the nice talk. It's interesting to get a status update. About the model, I guess it can't explain the charge current RD and RD star, for instance, because of the coupling and so on. Are there kind of reasonable extensions of the model that also explain RD and RD star?
Not that I'm aware of. I mean, you're right. The C prime by itself can't do anything about RD and RD star. In order to explain RD and RD star, you need some charged current effect. So you probably, I mean, it sounds to me like the only extensions of that model would be, very artificial. So you would need to introduce some charged current interactions. So you would need to introduce some W prime gauge boson, and it's hard to see how those W primes and the Z prime would be combined in a unified framework, which doesn't look very artificial.
Okay, great, thanks.
I had a question. So in your AFT analysis, you truncate the expansion at dimension 6. So for instance, ignoring tensor operators, which are generated at dimension 8. But if the new physics is basically the same order as the standard model, as you said, so you want kind of C9 to be 1 in the standard model, it's about 4. Does this truncation make sense?
Yes, so in that context, it does make sense because the standard model itself is very strongly suppressed by loop factors and CKM factors. So even though this dimension 6 is of the same order as a standard model amplitude, if you go to dimension 8, the suppression that you get is something like a mass of the B-meson squared divided by a new physics scale squared, and the physics scale is probably TeV, maybe even tens of TeV. So the dimension 8 effect is extremely tiny.
But I guess I mean when you have standard model plus new physics, you have the interference term and then you have the new physics term squared. And if
yes,
they're the same order, then the new physics term squared is kind of the same order roughly as the standard model contribution. But the kind of a dimension 6 term squared is the same order as interference between the standard model and some dimension 8 term. So
good.
Do you have to worry about that, or is there something wrong with this?
No, one doesn't have to worry about that in this context, because the important thing is that the relevant energy scale is the mass of the B-meson. So even though and on top of that, the standard model amplitude is not suppressed by the standard model amplitude effectively is also a dimension 6 operator in that sense, because you integrate out the W and the top, and you get a effective interaction which is suppressed by the electroweak scale. So your standard model and new physics are effectively coming from a dimension 6 operator, and you can consistently combine them, and you can even you can not only look at interference between standard model and new physics, but also new physics from dimension 6 squared, and you can combine that in a consistent way without having to worry about the dimension 8 new physics operators, which are much smaller.
Okay, great. That makes sense. Thanks.
Wolfgang, when you talked about the differences between B2K star EE and B2K star mu mu in the standard model, you kind of had a disclaimer that said that you had to take more care if you look at the angular differences, at an angular analysis where you compare K star EE and K star mu mu.
Yeah.
Does that extend outside somehow the very low Q squared region, or is this really just an issue in Q squared less than 1 GV squared or something like that?
That's a good question. I'm not sure. So I would be a bit cautious, but I haven't looked at that in the amount of details that would be required to make sure that you can just do this comparison at higher Q squared without worrying. So I'm a bit nervous about it, but it's more of an intuition than a concrete example that I could give what could go wrong.
Okay, I think there would be some very interesting work to do, because this is an obvious experimental direction to take as well. Because we can, within LHCb, we can use our high statistics muon sample to somehow drive the angular analysis in the lower statistics K star E sample.
Yeah,
and therefore get a direct result on the difference in the angular distribution, so to say. That's what we will actually measure, where we can get, again, a lot of uncertainties to cancel out. So
yes, but I think from the theory side, one needs to look at that in more detail.
Yeah, that would be very interesting to see if some progress could be made there.
Yeah.
Another question. Now in your plot here, you say, we can go down to 10 GV or whatever, but a lot of models really are discussing, things that happen at, TV upwards, whatever. Should we really change to use a language of a standard model effective theory instead of talking about C9 and C10, because we're talking of something that sits, beyond the electroweak scale? Or will we confuse ourselves?
I don't think it's necessary. So this language of C9 and C10, it works very well for PDKs, and I mean, people have worked out the matching of the standard model EFT onto this language of the C9 and C10, etc. And this is known very well. So one can translate those things back and forth without any problem. And I personally think, because the measurements and the B-mesons themselves, they live at this low energy scale. I think it's very appropriate to use the language of the C9 and C10 to do all of that.
Okay, I'm pleased to hear that. Thanks.
Okay. So I would say, since in the interest of time, since some people had to leave already, let's finish the official part and thank Wolfgang once more for an interesting talk.